Okay, let's go ahead and get started. So the
Projector scare, I think turned out not to be real, so I will just lecture you after today because it's working.
So I want to start by just reminding you sort of where we left off.
So we were thinking about optimization and finding the maximum and minimum values of a function on interval.
And we saw the extreme value theorem, which said that
A continuous function on a closed interval always has a maximum and minimum value. We also saw that the hypotheses were important. Right? So eliminate either continuous or closed interval and variables.
So you have to be continuous on a closed interval, and then you have the minimum values. And then we're also. Why do I feel like I'm hearing an echo? Are you guys hearing that too? Is it coming out of the? Just turn the volume all the way down. Okay, is the echo gone?
Okay, sounds good. So then we were sort of thinking about how to actually go about finding those values.
And we wrote down Fermat's theorem, which says that if your function has
a maximum or minimum at a specific value,
then either the derivative is zero or it doesn't exist. So sort of the strategy is going to be let's round up a bunch of keys for what the
maximum and minimum values.
Those will be
the endpoints of the interval, and then also all of the maximum and minimums.
And then
just what the values are on those candidates, and then take the largest value.
So let's write that down. So here's like how to find the absolute min and max. Of a continuous f on closed interval. So first thing we're gonna have to do is
find all of the places that could be
local maxes and mins. So those are places where the derivative is either zero or does not exist. So find all C such that f prime of C equals zero or does not exist. And then also are gonna have to look at so step one, find all of those values and compute what is f of those values. And then step two, we need to compute the value
of endpoints, but that could also be the maximum.
So we'll compute f of A, f of B, and then
largest among those numbers is going to be your maximum and smallest among those. So
of these numbers, the largest will be the absolute max. And the smallest will be the absolute min.
Okay, this strategy makes sense. So these numbers step one have a special name. They're called the critical numbers, or the critical value function.
So let me just write that down. So these are called the critical numbers. Maybe I'll just give a full definition for critical number just so it's clear. So a critical number the colors seem to so a critical number C for F is a number where either the derivative is 0 or does not exist. So just relating this to last time by Fermat's theorem, all
maxes will be equal numbers, but it's not true that all critical numbers are local maxes and mins.
So let me draw an example. So here's like a caution. Critical numbers are not always local maxes or mins.
So basically, the this will be a function that has like a in it, so it's not differentiable like point, but pink is not like a maximum.
So if I have something that's like a piecewise function, it's just a line up to a point, and then after that it's a line with like less slope. The function is differentiable here. So this with
a critical number, but it's not a local maximum or minimum. Okay, so to recap, the critical numbers may or may not be local maximums for just candidates, right? But all of the local maximums are definitely numbers. So by finding the critical numbers, we are finding like sufficiently many candidates for our maximums. But you have to once you find them, you have to think about what's going on at the function values. Okay, are there
questions? We're gonna do an example. Okay, let's do the example. So we'll find the absolute maxima and minima of the following function. So f of x is equal to 12 plus 4x minus x squared on the interval from 0 to 5.
Okay, so what are we going to do to compute the value of the function of two numbers, 0 and 5, and also to find all the critical numbers and the values of the function there as well. Okay, so other critical numbers we have two flavors. One is derivative of 0, one is derivative does not exist. Is there anywhere where the derivative does not exist for this? No. So
why is that? Well, it's a polynomial function, and we know how to take the derivative of a polynomial. It's going to be differentiable.
Okay, so
there is nowhere where we're not differentiable. Okay, so let's find where f prime of c is equal to 0.
okay, and that'll be our candidates for some of our experts for So
this is pretty easy. So all we have to do is take the derivative of this function. So let's find f prime of x.
what is that going to be? Yes, so 4 minus 2x.
And then we just want to find where this is 0. So we'll set 4 minus 2x equal to 0 and solve for x. Okay, so we get negative 2x is equal to 4, and then dividing by negative 2, we get x is equal to 2. Okay, so that one candidate for the maximum or minimum value of the function. So let's compute.
Maybe I should pause for a second. Does this make sense? Why we wanted to this calculation went? Okay, so then I'm gonna f of
u. So this is going to equal 12 plus 4 times minus 2 squared. So we get 16 is the value at 2. Okay, so this is like candidate number. So I'll just circle it so we can compare it easily later. Okay, so then our other two
are going to be the two and 0 and 5. So this dispute f of 0 and f of 5.
So we also need that. Maybe I'll do these on separate lines though. Okay, so f of 0 is 12 plus 4 times 0 squared. This is just 12. And then f is 12 4 times 5. Oh, sorry, this should have been a minus. Well, it doesn't matter, but it's minus 5 squared. Okay, so 12 plus 20 is 32 minus 25 is 7. Okay, so here's our the pink is our list of candidates. For absolute maxes and mins.
Okay, so then from this we see that 16 is the maximum value of the function interval, and 7 is the value of the function interval. So
the absolute max is f of 2, which is 16, and the absolute min is f of 5, which is 7. I think this is kind of neat because we didn't really have to know anything about what function looks like in order to figure this out.
You just went ahead and did the derivative and found where it was zero, and then from there we were able to determine
the maximum and minimum values without ever having to look at the graph of the function.
So that is kind of cool. Are there questions about this example? We're gonna do another one sort of more like a word problem. Okay, so let's do
the word problem sample. Okay, so the situation is that we have hundreds of fencing material. So like something to build a fence out of, and we want to find the largest rectangular area that we close with that amount of material. Let's say 100 feet of fencing material. We want to know what is the largest area. Or sorry, I should say rectangular area. That I can enclose.
Have you guys heard folks that are along the line like a mathematician that's been an engineer, something, and this is the outcome. Some of you guys are not. Okay, so there's one along lines, which is a mathematician and an engineer are asked to they're given 100 pieces of material and they're asked to enclose the largest area that they can. So engineers sit down and solve a problem and produces. Well, I won't tell you the answer. Ever get to this question. The physicist is like, okay, well, the largest is going to be a circle, and this fence to be a circle, and that will close the largest area. And the mathematician just makes whatever fence they want to, and then they just like the outside of the outside of the fence inside. So that's but anyways, so the optimization problem. There's like tons of these, and they're all pretty funny if you look on. Another one of my favorite ones is a mathematician and an engineer are staying in a hotel room, and the fire alarm goes off, and the what is that? The engineer wakes up, sees the fire, calls the building, the physicist sees the fire, does a quick calculation, not that they need like one bucket of water to put out the fire. And the mathematician fire goes to the bathroom, lights a match, puts it under the faucet, says, it works, back to sleep. I find these, there's tons of people to look up for. Okay, so you guys have any guesses about what shape the rectangle will end up being? Like what the long rectangle or like a square? Yeah, I think that would be like it'll be one of the two, right? But you think about it, like one of the extremes is like if it's really long and skinny, it will have no height and will enclose zero area. So maybe the best guess is a square. And that actually will turn out to be right. So here's how you do this problem. So let's draw
And for now, the two sides, x and y.
And later we will find what y has to be with x.
So here's how we'll do this. So I'll label all the sides of the rectangle.
So we know that the perimeter is going to equal 100 feet.
So I know that the perimeter is x plus y plus y. So 2x plus 2y. And this has to equal the amount of fencing material that we have. So
using this equation to start, I will solve for y in terms of x, and then I will get a rectangle that just has side labels and x. So we don't have two variables anymore.
So let's solve for y. So we'll get 2y is equal to 100 minus 2x. And then I'll divide both sides by 2. So I get y is equal to 50 minus x. Okay. So I will take this and substitute that in over here. So y is equal to 50 minus x. Okay, so now
what is the area of the rectangle gonna be? Yeah. Yeah, exactly. So the area of the rectangle is just times height. Originally this is x times y, but we know that y is 50 minus x, so it'll be x times 50 minus x. Okay, and this is the quantity that we are hoping to maximize. So we want to find the maximum value of that function for x's within some interval.
So here's I'm gonna call this function a of x. So now our problem is to maximize a of x, which is I'm gonna just expand this out a little bit. So 50x minus x squared for x's.
What should the interval? What are our possible values of x? So we only have max functions on a closed interval. So what shows closed interval space?
Yeah. So we'll just set this to be 0 to 100. So just thinking about problem. Like we have 100 feet of fencing material. So this side length could be equal to 0, or it could be equal to no, we don't have enough fencing material to make it 100, right? Because then we need 200 to make the full thing. So we can only do 0 to 50. Does that make sense?
Oh yeah, 0 to 50 for the possible outside values. Okay, so
let's maximize this function. So I need to find. Okay, so this function is going to be differentiable everywhere. So there's no points where the derivative doesn't exist. So I'm going to take a prime of x, and then I'll set that equal to 0. So okay, this is 50 minus 2x. So this is 0 when 50 minus 2x is equal to 0. So when 2x equal to 50, so x is equal to 25. Okay, are we?
So then, I also need to check the endpoints. So I need to
find, or I'll just look at. Here's our candidates. F of 25, or sorry, I was calling it A. A of 25, A of O, and A of 50. Okay, so A of 25 would be 25 times 50 minus 25, which is 25 squared. Whatever that is. A of 0 would be 0 times B minus, which is 0, and then A of 50, 0 times, or sorry, 50 times 50 minus 50, which is also. Okay, so that tells me that this one is the winner. So the area is maximized when x equal to 25, and the area would be 5 squared. And if you think about our original diagram, let me go back to this. If x is 25, then y is going to be 25. So we get a square area. Okay, are there? Okay, so that's sort of optimization stuff. So there's a lot of talk about the web work that and they'll ask you like about finding numbers of functions and also finding maxes and intervals. Okay, so now we're gonna shift about something called the value theorem. And this is like a theorem that has a lot of really applications, and it's one of these things that's like it comes up in unexpected ways a lot of the time. So it's a really cool theorem, and I'll show you basically what it's saying. So basically what it says is, let's say I have a function define those intervals, so like from A to B, and then it does something little like that. What this is saying is that if I draw a line between these two endpoints, this has some slope. And what the mean value says is that there is some point in the middle where the derivative has that same value. So either is a tangent line to that has this slope as this slope going to the two points. So I can kind of estimate it right here. So it might be something like that. Is like the value that the theorem guarantees. So that's sort of the picture. Does this make sense? Sort of on a level. So what we'll do, we're gonna fix this, and we will do it in a few parts. So the first part is something called Rolle's theorem, which is basically the mean value theorem, but you assume that the two endpoints have the same value, so that you're just finding something that has a slope.
somewhere where the function is zero.
So let's state Rolle's theorem. So first step is Rolle's theorem. So here's what Rolle's says. We're gonna suppose f is a function satisfying a few hypotheses. So first we want it to be continuous on some closed interval.
It is again that this interval is here.
So we're assuming that it's continuous on a closed interval. We're also going to it's differentiable. On the interior so the open version. And then
Also going that it has the same value as two endpoints.
okay, so then the conclusion of the theorem is that there is
a point in the interval. In the interior of the interval, it'd be such that the derivative is there.
So there is a C in A to B such that f prime of C is equal to zero. Okay, so here's some pictures to keep in mind. So you could have something like this. Okay, so this is saying
somewhere in here. If I start at the same height and continuous and differentiable, then somewhere has to be a point where I have
derivative equal to zero. So the tangent line must somewhere have slope of zero. You could have if your function is more wiggly, you could have more points where this happens, so you could have something like that. And then you have multiple. And it could also be something down instead of up. So you could
If your function is either non-US or non-differentiable, then obviously you can avoid this. So if you're not continuous, for example,
so here's a picture for why you need continuous hypothesis. So if we start here and here, like we could just have a line going to some hole and then goes back down, back up.
Okay, so that doesn't have this is a
not continuous example. And so the theorem fails. And then a not differentiable example is something that looks like a value function. So we just go down, and turn around. And this also fails because it's not differentiable.
Okay, this statement of the theorem examples makes sense for questions. Okay, so what we're gonna do is a theorem, and basically we're going to use extreme value theorem that we already have that says if I have a continuous function defined at a finite interval, then it's a maximum value. And then we also have for Mauss theorem, which says that the local maximums will have either be non-differentiable, which is we will have or have the derivative zero. So let's line those together to find that there must be places where the derivative zero.
Okay, so here's the proof. And we're gonna break this into cases. So one is if the function is constant. So if f of x is equal to some constant. Well,
The derivative is zero.
So that means
that number C from the interior will satisfy we will have found a C in A such that f prime of C equals zero.
So take any C in AB, then f prime of C is equal to zero. Okay, so that case,
It's pretty easy. Other questions? Okay, so the second case
that we have to look at is we'll just assume
there is some
value that there is inside of this interval where the function is larger than either of the two endpoints. Okay, so in that case, we searching for a local maximum inside of the interval. The flip side of this is somewhere I am lower than the value to endpoints than for a local. So that would be this that case to handle this picture. Picture is like cases. So let's suppose. So here's my suppose for some x interval b, I have that f of x is greater than the value of points, which is equal
f of a.
Okay, so
by extreme value theory, I'm getting a max value function inside the interval.
I'm just gonna abbreviate EVT, so extreme value theorem. F has a maximum in the interval AB.
We already know that somewhere the function has a value larger than the value of 10 points. So that means that max has to be something on the inside of the interval. So it has to be a value of the function.
So this must happen inside the open interval. So the maximum occurs at a critical point in the interval A to B. But
since function was assumed to be differentiable on the A to B, we know that
So critical
points
can
can
only
only
either be derivative does not exist or derivative is
zero,
zero, and the derivative in this case doesn't happen. So since f is differentiable on this interval from A to B, the critical point must be one where f prime I'm gonna call this name this critical point C. So the critical point C must be one where f prime of C is equal to 0. And that finishes this
this shows that somewhere in the interval there is that somewhere in the interval there is a derivative of the function is zero. Derivative of the function is zero.
So that
That
finishes that case.
Are there questions? Okay, the other case is exactly the same, except that f of x is less than f of a somewhere, and then by the ABT f has a minimum on a so on and so forth. So everywhere you just plug the inequalities and replace maximum by minimum. So
the third case, we suppose for some x in AB, we have f of x is less than f of a. And this case follows similarly to case 2.
Okay, so that is the Rolle's theorem.
Are there questions? Yeah.
Where's the interest?
Exactly. So the mean value theorem will have a lot of different applications, and like that will just specific problems that you can use it to help find value where the slope is equal to the slope of that endpoint. But then it also will be used to prove other things. Good. Other questions? Okay, so let me also mean value theorem. I don't think we'll have time to today, but I'll sort of picture that explains how it is proved. So here's the mean value theorem. We'll have similar hypotheses to Rolle's theorems. We'll let f be a function with we're gonna assume that f is continuous on the interval from A to B, closed interval, and it needs to be matchable on the interval from A to B. Okay. Then what this says is so. Let me draw a little sketch over here. So we have A and B.
So this here is at height f of a, and this is at height f of b. So what this is saying is then there is a C inside of the open from A to B, such that the slope at the slope of the tangent line to the function at C is equal to the slope of this line between the endpoints.
So write that down. That's just gonna be rise over run. So f of a minus f of b
divided by b minus a. Okay, so that is the statement of the theorem.
And roughly how we're going to finish this is next time we will define a new function which we will be able to apply Rolle's theorem to. So in order to do that, we're going to have to take this picture and kind of unslant it. So what we'll do is subtract
from my function f. I need to subtract this function defined by this line, and then that will untilt so that we get something to apply Rolle's theorem to. Okay, so we'll do that next time.
Remember that the extra worksheet is due tomorrow at night. If you want to do that to get extra credit for the midterm. And you can come to office hours or you can tell our scholars that.
And I'll see you on Friday otherwise.